Okay, welcome back, everyone. Today's afternoon session, we have two 25 minutes talks, plus 5 minutes for each questions for each talk. So they asked me to stay here because Zoom people should see us. So the first talk is by Shuddha Brahma on quantum gravity in de Sitter space. So yeah, take it away.
Thanks. Thanks to the organizers for this invitation. And I'm going to present, so I was asked to talk about quantum gravity in de Sitter space, and I'm obviously going to talk about some of my personal perspectives on it by this rather provocative title. I really don't mean this equals, I just mean that there's a lot to be learned from quantum information techniques, and we have learned a lot about quantum gravity from using them in black hole spacetimes, and perhaps there's a lot to be discovered from using these tools in de Sitter space as well. So most of this work is done with Robert Brandberger, Arjun at Edinburgh, and some PhD students, and also some ongoing work with a French group and Lucas Hackle in Australia. Good. So I think I'm not going to justify the use of de Sitter space. I think we all agree that that's something that is useful to describe the very early universe as well as late-time evolution. But I still perhaps need to justify a little bit why do we even talk about quantum gravity in de Sitter space, because if we are really interested in describing the evolution of the cosmos as a whole, we are talking about larger scales. Why do we even need quantum physics? And of course, a canonical example is that the widespread or the mostly popular paradigm of the early universe is inflation, which not only solves, as we know, the standard cosmological problems, but makes a rather remarkable prediction, which is to say that it explains late-time inhomogeneities as we can observe them as temperature and isotropies in the CMB as originating from quantum vacuum fluctuations. So this is a very rare test bed for testing quantum mechanics. But we can think we can be more ambitious, think bigger. We can think that the quantum origins of space-time itself has to do something with entanglement. And this is a very popular theme, of course, as I mentioned, in black hole physics over the last decade or so. And is there a description of this in de Sitter space? Can we think of de Sitter as emerging from quantum entanglement of some boundary degrees of freedom? Again, these are just cartoons. I don't get to show a lot of nice pictures, so I'm putting them as much as possible in the first slide. So this first point here, the main message I want you to take away is that observations always access parts of Hilbert spaces. So that just means that whenever we are looking at some part of a Hilbert space, our system density matrix is a reduced one, and that we need to incorporate dissipation and decoherence. There's a very nice talk by Beilok Hu yesterday, and also some very nice talks about this in some of the parallel sessions. So so this is very common. This is common to physics, I would say. What is remarkable to cosmology is the nature of the environment. Typically, this is not the kind of environments that we often encounter in condensed matter physics and so on. And I'll describe this in a little bit more detail later on. In particular, that there's a phenomena called non-Markovianity, where there's a history dependence of the state, where the state came from, that creeps into due to this special environment in cosmology. For the second point about the quantum origins, I'll restrict myself to a very particular thing that I've just become very interested in only very recently, which is complexity as a quantitative measure of the difficulty of constructing this required EPR entangled states, which would be able to explain de Sitter from this holographic degrees of freedom. So I'm going to say a little bit more. I'll explain some of these terms as I go along. So concretely, for the first part, I will consider open quantum systems approach to inflation. That would mean that I would have to consider open EFTs. And that, in particular, I will look at this momentum space entanglement entropy as a quantifier for non-unitarity in the theory, or non-unitary evolution in the theory. For the second part, I will examine this new proposal by Strominger and Cottrell about cosmic version of ER equals EPR, and show that there is a way to actually compute the complexity of this EPR state. And that reveals to us some very nice features of this state, that it is indeed, there's some evidence of this cosmic version of ER equals EPR. So if you fall asleep right after this slide, this is the take-home message, which is quantum informatic tools such as entanglement, entropy, and complexity they seem to be providing us with some very unique and rather unexpected, I would think, insights about quantum gravity. And I could have stopped it there, but because this is something to do with de Sitter space, in particular, I'm a cosmologist. I'm interested in what they have to say for de Sitter space. Also because many of these tools can be verified from explicit string constructions in the case of ADA space. But in de Sitter space, we have to do a bottom-up thing. We don't have string theory to help us. So it's really perhaps in this particular arena that these tools would reveal more to us, even more to us. All right, so the first part, which has to deal with inflation as an open EFT, yeah, again, just for pretty pictures, I'm looking at this cosmic inflation, this very early part of the evolution of the cosmos. So the general idea I think all of us are familiar with is that we thought we would look at higher endpoint functions and non-Gaussianities, and they would tell us about the physics of the very early universe. Only one problem, we have not observed any yet, so perhaps we need a little bit of a fresh perspective. And one such perspective which came out of this is this cosmological bootstrap program where people take symmetries and principles such as unitarity and locality very seriously and bootstrap all these endpoint functions from these principles. I'll take a complementary view and of this open quantum system applied to cosmology. And in particular, as I already mentioned, observable degrees of freedom in the universe are always necessarily part of a larger system. And modes of, in short, modes of interest, of physical interest, are coupled to an observable stuff, usually. Why is this the case? I'll give you two examples. In this case, typical UV completions of inflation require some additional fields. So we have like some higher, I mean, the field space is not typically one-dimensional if you want some UV completion for inflation. Even though at low energies, it might look like a single degree of freedom. So that these would be examples of UV degrees of freedom to which the inflaton talks to. Whereas also typical models of inflation predict much larger number of E-foldings, like let's say order 500 or 5,000 orders of E-foldings, which means that there's a lot of long wavelength modes in the universe. If this small box is the Hubble patch, is our Hubble patch, and we can only observe these blue fluctuations, there are still these very long wavelength fluctuations which we can never observe directly, and yet they do matter. I mean, our observations do depend where we are with respect to these long wavelength modes, if there is some significant mode coupling. So this is an IR example. These are IR degrees of freedom which our degrees of interest are coupled to. And Wilsonian EFT does not quite directly apply to cosmology. There are many ways of seeing this, from the Feynman-Vernon influence functional, as Belloc was mentioning yesterday, but also like generally because there's no conserved quantity like energy that we can integrate out, and that is not true for cosmology. So what this non-unitarity is nothing to do with quantum gravity. This is a very bottom-up, very an approach that is built on like very well understood physics. We're just looking at some Hilbert space which has some density matrix evolution on it, evolves on this, and we're just tracing out parts of the Hilbert space that we have no access to. So we have some reduced Hilbert space for the system degrees of freedom. The only thing here is that this reduced density matrix can exchange energy and lose information to the environment. So this is what I meant at the very beginning by incorporating dissipation and decoherence. And it is by now it's well known that both of these things are not just conceptual things, they affect observations. Whether they affect it significantly or not is an open question. And this evolution, the evolution equations for this reduced density matrix are commonly referred to as master equations. These are very well studied in quantum optics. For example, these are known as these Lindblad terms. So these are non-Hamiltonian terms which denote this dissipation, which tells you the system can just dump or borrow energy from the environment. However, and this was also like, people have studied this. I'm not coming up with all of this right now. For instance, Arjun, my colleague at Edinburgh, studied warm inflation, which assumes that there's some thermal environment. And many other cold inflation, typical models of inflation just ignore dissipation altogether. The main punchline of this part is that the environment is neither stationary nor thermal, which means that it's somewhere in between, and the Lindblad theorem doesn't quite apply. So the master equation is this Nakajima-Zwanzig type. That's essentially because of having an out-of-equilibrium environment. So we need some non-Markovian master equation, which needs to be solved for this system degrees of freedom. Again, I have not mentioned everyone who has worked on this for some time now, but Cliff Burgess and Sarah Shandera and my collaborators in Paris, they've been working on it for quite some time now. These master equations are helpful for many things, including resumming late-time secular growth. So, in gravity is a system, if you couple something to gravity, there's no way to turn it off. So unlike in collider experiments, where you can have collisions for a finite amount of time, you have free particles at the beginning, free particles at the end. In gravity, if you couple things, even if they're free at the beginning, there's no way to turn off gravity, which just means that the perturbation theory naively fails because of this kind of secular growths in cosmology. One way to deal with them is this dynamical renormalization group method. There's many other, and one way is also this evolution master equations. There's a way to resum them and go beyond the standard perturbation theory. That is what I mean by SPT here, and resum results. This is not something I'll talk about, but this has a lot of this part has a lot of consequence for infrared for infrared modes in cosmology and back reaction in cosmology. Of course, because I'm giving a talk on de Sitter, so I'm only restricting myself to quasi-de Sitter or inflation in this first part, but these techniques are not, of course, exclusive to that. If you have any other model of the early universe that is your favorite, say pyrosis, which also deals with quantum fluctuations, you can still apply open QFT techniques and get some nice consequences, like we put some bounds on the energy of the bounds and so on. Right, so what am I talking about in a little bit more detail? I want, in particular, I just take single field slow roll inflation. I want the short wavelength modes of this to be my environment and the long wavelength modes to be my system. So modes which are super Hubble, as the modes which exit the horizon, those are the things that we observe later on. And the short wavelength modes are these high energy degrees of freedom which I will integrate out or trace out is the right way to do it in this case. I consider a coupling that arises simply because GR is nonlinear. So there's no way to avoid non-Gaussianities. They can be so small that we cannot detect them, but there's definitely nonlinear terms. I take one such term from the cubic nonlinearity. And if you have some other model which is your favorite or which you think is more natural, such as DBI inflation and so on, anything that we derive for this model is sort of a lower bound. You put any more interactions that will give you more entanglement or more decoherence and things like this. So this is my picture. The red band is my system. The blue band is my environment. There's some quantum gravity theory that I'm not going to be bothered about. I'll just take for granted that this quantum gravity theory can deal with the Transplanckian modes, and I'm not going to worry about that at all. All right, so the goal for us is, can we construct some bottom-up open EFTs? We know how to do EFT of inflationary fluctuations. Can we do open EFT of inflationary fluctuations, which will also take into account these effects of decoherence and dissipation? I'm not claiming that I have solved this, but this is what we aim towards. And then we want to obviously estimate effects of such non-unitary evolution on observations. Do these really have any effect on observations, or are these just conceptual things? Good. So as I already mentioned, I'm going to consider momentum space entanglement in this part of the talk, because I'm going to consider bands of momenta as the subalgebras in which to define the subsystem, and I'm going to trace out over this high energy or this high momentum modes. So what I'm calculating here is perturbative momentum space entanglement entropy to leading order in perturbation theory, and this is a quantifier of this non-unitary evolution for me. And I'll follow the notations in this paper. This is the case for scalar QFT in Minkowski space, because that's what I want to start out with. That's the canonical example. And you get a result that looks like this. So this is leading order in lambda. Lambda is a dimensionless coupling parameter. So you need some interaction Hamiltonian. If you just have quadratic Hamiltonians in momentum space, the entanglement entropy is 0. And this is the leading order term. And this is easily calculable because this is written in terms of matrix elements, which you can calculate in perturbation theory. Good. So what about if I want to try and do this calculation for quasi-de Sitter? We tried this with Robert and a master student a couple of years ago now. And what we find is that there has to be some generalizations. First of all, there's a lot of squeezing going on. So that's this time-dependent de Sitter background which creates particles. That's the squeezing effect. The Hubble horizon is a natural scale to demarcate between long and short modes. That was already in my diagram that I showed you. And again, the cubic interaction doesn't have to be something by hand. That's something given to you by gravity. But of course, the interaction that I showed you earlier implies that we need now time-dependent perturbation theory to calculate these matrix elements. And that's what we need to do. So you find that you need to do some integrals which are rather complicated, and you cannot do them analytically. or at least that's what we thought back then. So we had to estimate them, and we found that this integrand is dominant in this what cosmologists would call the squeezed configuration. So you have 2 environment degrees of freedom and 1 system degree of freedom. So 1 long wavelength mode and 2 short wavelength modes. And this is the result, which is that the entanglement entropy per unit physical volume is something that scales as the Slow-Roll parameter, the Hubble parameter, and the mass Planck. So after doing this calculation, if I was clever enough, we figured out that, and if we could figure out that the squeeze configuration would matter more, which we could actually from some arguments, this you can get from power counting, everything in blue. So that's not a surprise at all. What is rather surprising is this very fast growth of this entanglement entropy. Again, remember this momentum space entanglement entropy. And this was verified later on with my students for just having a spectator field with a cubic coupling in de Sitter. So why do we always find such a large growth in this perturbative entanglement entropy, and how fast is this growth? To compare, to get a measure for how large this is, you can compare this with some background quantity. Let's say the coarse-grained reheating entropy, this thermal entropy, or some Gibbons-Hawking entropy. And you find that this quantity, which is a perturbative quantity, that's evident from this epsilon and so on. This grows very fast, and actually around the scrambling time of de Sitter, it becomes almost equal to this reheating entropy, this thermal entropy. Now that, to me, sounds like there's a breakdown of perturbation theory. That's not entirely surprising. Starobinsky told us about this many, many years ago. What is a little bit surprising to me, however, is the time scale. I would have imagined that this breaks down around like the de Sitter entropy, which is not the logarithm in here. The logarithm makes it very, very fast when these perturbative methods seem to be breaking down. So what do we make of this? So if you ask Robert, he would say, like, that's perfect. That's the Transplanckian time, or WAFA, and they would love it because that's some evidence for the swampland. I'm not that ambitious. I'm just claiming that this perturbative expansion is not trustworthy after this time. But then there's a puzzle. We know that loop corrections do remain under control. There's a lot of people, including people in this audience, who have done these loop calculations, and we know that they remain under control. So the EFT of inflation clearly applies. Is there a way that maybe the open EFT of fluctuations do not? So by that I mean, is there some dissipative effects and so on, which we've ignored? That is the reason for this breakdown of perturbation theory. So we tried checking this. So we calculated the 1 loop correction to the graviton propagator during inflation due to graviton 3-point functions. And you find a result which is exactly what you would expect from, or what you expect from standard loop corrections. But we started out with a Markovian master equation. So that's an assumption on our part. We started out with a master equation that is Markovian. And then we find a result for this loop correction, which is exactly what you would expect for standard methods. The standard in method is what I mean. And what is nice is that this exactly matches. But then we can go back and check whether this Markovian approximation was a good one. So we can check what is known as the dissipation or this memory kernel for the environment degrees of freedom. And for a Markovian behavior, you need this memory kernel to go as, which has to be delta function peaked in time. It has to be time local. However, when we check this, we find that this is quite sharply peaked. So it goes as some power of 1 over tau minus tau prime. But it's not delta function peaked. So there are deviations from Markovianity, from strict Markovianity. Now, why did we not use this dissipation kernel to do this in the first place? Why just go back and check that it's non-Markovian? Well, because it's very difficult. So we have to systematically estimate effects of non-Markovianity. But there's a chance that would give rise to some novel phenomena. This is already found by my French colleagues, who found that there's some novel phenomena such as recoherence, which you find if you consider the non-Markovian master equation. At a linear order, you can exactly do this. You can exactly solve this equation. You find there's some really novel phenomena which is specific to a curved background like de Sitter, as well as using these non-Markovian master equations. And we are trying to check whether this stays there or whether this persists beyond the linear order. So linear order is obviously a toy model. We want to go to non-linear order to check that. So Markovian environments are pretty difficult to get in cosmology for many symmetry reasons and so on. So we have to check the effect of non-Markovian effects, and maybe that does affect the decoupling of UV modes. That would have some resonance with the Transplanckian problem of inflationary cosmology. Maybe that's where it comes in, and this decoupling doesn't happen as smoothly as one would expect from Wilsonian EFTs. All right, so how am I doing with time? Pretty well, okay, good. So now I come to the second part, which is a bit more ambitious, and which talks about the emergence of de Sitter space itself in some entangled state. So this is something very new to me. I'm not an expert, and I realize that all the holography talks are tomorrow. So I'm just going to flash you a slide to tell you about, like, just the slogan, which is this ER equals EPR, that just says that, you can construct the full bulk black hole state from entanglement between boundary degrees of freedom. And this is like the cartoon for this, I guess, which is showing that if this entire wormhole solution comes from entanglement between these boundary degrees of freedom, and if you don't have this entanglement, then there's no wormholes. All right, so this state is rather special in this context. This is the state at time t equals 0, this thermophile double state that defines these bulk states in this double-sided ADS black holes. So what I want to focus on in particular, so I'm guessing you'll hear more about this tomorrow at the plenary sessions. So what I want to focus on is this very limited point that we already know for, again, 10 years now, that although entanglement entropy and this RT formula for entanglement entropy is the main evidence we have for this slogan, we also need to go beyond entanglement. And that's just because quantum states continue to evolve after thermalization, and Susskind proposed that maybe complexity is the right measure to quantify this. So the way I'm going to think of complexity is in this terms of this computational complexity or circuit complexity. And I'm going to say that this is what quantifies the difficulty, which is like a hand-wavy way of a high-energy physicist way of saying what this is, to construct an entangled state from another rather simple factor state that we start out with. And in particular, I'm going to look at de Sitter space. Of course, that's the interesting bit for me. So I look at de Sitter space, but in this rather weird hyperbolic slicing, and this is also quite well known now. And if I define a wave function in the space like hypersurface everywhere, I define a wave function of the bulk. So I have to define my Euclidean vacuum or Bunch-Davies vacuum everywhere on this dark shaded line. And this L and R regions, just remember this, is bifurcated into two left and right regions. So what's interesting is that I will start with a state, that is this factor state, the vacuum in the L and R regions, and neither this L vacuum or this R vacuum are states in the de Sitter Hilbert space, because they don't have de Sitter symmetries. But then we can write down the Bunch-Davies as an entangled state over this L and R vacuum. What is nice is that, so this expression is not important, this is this Mij appearing here, but what is nice is that all these L, R, and Bunch-Davies states, these are all Gaussian states. That's why I'm able to apply complexity as this minimum geodesic on space of unitarities, this idea by Nielsen, with choosing some appropriate cost function, which was used by Myers et al. For this black hole case. So if I use that, I can actually compute the complexity. That is a very difficult thing to do if you have some non-Gaussian state here. When you do this computation using this covariance matrix approach, which I won't go into, you find that you get a result that is actually finite. You can't do this integral analytically, but you find that this integral is convergent. You can do this numerically. This is a finite thing. This integral is finite. And this is also proportional to a volume, which is like one of these holographic conjectures for complexity. We are not using that holographic conjecture. We are computing something in field theory, in quantum field theory, a complexity, and we are finding that it bears out the holographic expectation. So why is this surprising? So what we find is the complexity of this de Sitter vacuum is finite both in UV and IR. The UV part is not that surprising because we are considering entanglement between, this is long-range interactions between parts of space-time which are disconnected from each other. Contrast this with the complexity of the Minkowski vacuum of this thermophile double when you compute it from this ultra-local vacuum. When you put QFT on a lattice and you compute this complexity, that's a divergent quantity. However, this one is finite, which means that although this L and R vacua don't live in the Hilbert space of de Sitter, this Bunch-Davies vacuum, which is of course a bulk state, it lives in this HL tensor HR Hilbert space, and I can construct it with finite complexity. This is not I don't need infinite complexity. There's no divergence with respect to some cutoff. As I already mentioned, this bears out expectations from holographic conjectures. And this was already shown by Reynolds and Ross that just by the symmetries of de Sitter, if you believe in the symmetries of de Sitter and you apply the holographic conjecture, you expect the complexity to go as 1 over eta cubed. That's what we find. That goes of the volume of this hyperboloids. But we do this as an explicit field theory computation again. This free scalar restriction is important because as I said, if you go to non-Gaussian states, we don't know how to compute complexity. And for our choice of reference state, the complexity seems to be a universal quantity. So this is not something that I emphasized here, but if you look at this transformation, this depends on the momentum as well as this nu, which depends on the mass of the scalar field. But in the complexity, the nu just falls out. I don't know why that happens, but it seems that it's a universal quantity and it's independent of the parameters in Lagrangian. The only parameter is the mass. It depends on the geometry of space-time. It depends on the Hubble parameter, but it doesn't depend on the parameters of the scalar field Lagrangian. So this proposal so I'll go very fast on this because I'm told I have one more minute. I can tell you more about this in the discussion session if this is not clear. So Strominger and Kotler proposed that there is a version of ER equals EPR, which we can do if you believe in this DSCFT as the dual CFT living on Scri+. So the caveat is that this result obviously has nothing to say about static patch holography or other forms of holography that people use sometimes in de Sitter space. But if we identify these L and R states with this boundary CFT, with the vacuum of the boundary CFT, like Strominger does, he uses a different basis. He uses this quasi-normal mode basis, whereas I'm using this hyperbolic de Sitter slicings. And there's a way, by the way, to go from flat slicing to hyperbolic, as shown by Maldacena. So if I identify this L and R with the vacuum of these boundary CFTs, then the bulk state, or this Euclidean vacuum, can be shown to be a thermophile double state between these boundary CFTs. And this you can show. Of course, I can't show this because I don't have time. And of course, this was already shown that from this state, if you trace out over the R region, for instance, you exactly get a thermal density matrix for the L region as you expect. And this was already shown by Maldacena, but not that you have a thermophile double state if you identify these things with things in the boundary of this de Sitter space. So this is the main statement, that the Hilbert space of de Sitter space is the tensor product of the Hilbert space of this CFT. So I have, unlike in the area CFT, where you have one CFT on the boundary of area space for de Sitter, and this proposal is of course not due to me, but Strominger, that you need two CFTs on the boundary, and the entanglement between them produces all the bulk states. So I think this hyperbolic slicing is just cleaner, and each of the CFTs just correspond to two of the hemispheres of the S3 on the Scri+. So that makes this a slightly cleaner picture than the quasi-normal mode basis, which I have a little bit difficulty understanding. So I'll just leave my conclusions over here because I'm running out of time. Just mentioning that also this kind of complexity and entanglement plays a crucial role in emergence of space-time in other models, like such as matrix models of string theory, and I work a lot on those with Robert and Samuel. And there's a lot of things to be checked. We checked already that you can use the same methods to think of Minkowski vacuum as an entangled state over the Rindler vacua. And this was already mentioned by, again, Strominger, that this should work, and we've checked that this does work. And this seems to be a very generic feature that whenever you have some killing horizon separating two regions and the entanglement between them produces some bulk state, the complexity is finite, and it's independent of the parameters in the Lagrangian, and depends only on the geometry of space-time. All right, sorry, let's stop here.
Okay, thank you very much for the nice talk. So we start the questions. We have 5 minutes. Please wait until I bring you the microphone. Let's get my exercise today.
I'd like to ask you about the comment of the tensor loop calculation of the graviton propagator.
Right.
And you mentioned that it agreed exactly with some other results, one of which I was in, and I don't understand that statement. So the 2020 paper was with Nick Tsamis and Lin Tan and myself, and also parenthetically, I don't think anybody else actually did the full-blown quantum gravitational calculation of the graviton two-point function. Are you sure you have those other references right?
Yeah, you're right. I think all of those references, to the best of my knowledge, like I couldn't find a reference which does graviton loop corrections from gravitons itself. So when we started out this work,
I did. The 2020 did.
Yes,
I don't think those other ones did.
What I'm trying to say is that those sometimes people use like conformally coupled scalars and other things, but this general.
So it wasn't tensor loops like you said.
It
right?
was. So that's what I'm saying. So it matches in the sense that we expect the general corrections to be of this form of this soft.
But that wasn't. I'm not sure what delta sub t squared represents. But if you're talking about the graviton self-energy or the graviton mode function, we didn't get anything that looked like that at all. We got corrections that went like g h squared rather than g squared h to the 4, and we got terms that involved that showed secular growth, like logarithm of a. How do you reconcile this? You're using the language in some way I don't understand.
So the secular growth story is something that I tried to avoid, so I didn't mention it here, but I think I have a backup slide on this. So we try to see that there's some secular growth, and if we can if we can just resum that, and that's what we find, that we can calculate it to one relation.
The one-loop calculation shows it.
Yeah.
Whether or not you can resum it, and I don't, by the way, accept those other authors' statement about resumming it, but whether or not you can resum it or not is independent of the statement of what you actually get when you do the calculation. When you do the calculation, I swear to you, you get a logarithm of a.
I agree. So I think there are two answers to that. One is that I was avoiding questions of the secular growth, so that's not something that I was focusing on. I was just focusing on how it depends on the renormalization scale. But the other question, to answer your question, like you can also redefine your power spectrum, as you probably know, using the 4-point function, and so you use a term from 3-point and the 4-point function, and you redefine your power spectrum, and then this goes away.
That's Sinatorian Zaldaryaga stuff, and if you check the literature, you note that I made I thought a pretty devastating criticism of that, and that is that if your point is just that you can turn off any loop correction, guaranteed you can do it. You can define a field redefinition. I can give it to you explicitly, which will eliminate any correction at all to the power spectrum. The question is it the thing that we observe? They did not make a compelling case of that. Nobody has made a compelling case of it. It's an open issue, one that I wish we would talk about realistically as scientists, and one which dogmatic views on that subject are inhibiting an informed discussion.
So I'm just making a comment that if I ignore the secular growth, this is how it scales at the renormalization. I don't understand your comment about the power counting. I thought that was obvious if I use a graviton 3-point function, but we can maybe discuss this in the discussion session.
Yeah, let's keep that for the discussion session. We have time for one quick question there. Okay. This one. Did you turn it off? Yeah, that's good.
Yeah, thanks very much for the very nice overview talk. So I just have a quick question on the complexity calculation, where you say that you get finite complexity. So I guess complexity is not only defined with respect to reference state, but also with respect to choice of operations you're allowed to do, which somehow is probably encoded in the space of unitaries that you integrate over. But then you were referring to somehow long-range interactions. Are you allowing for something like long-range operations in your definition of complexity?
Yeah. So in this particular, you're right, absolutely. But in this particular case, it's much restricted because these are just Gaussian unitaries, right? So somehow the norm on this space of Gaussian unitaries, which is some SL2R algebra, that, well, it's not unique because you have to choose a cost function, but that defines the complexity. Now the long-range interaction story is just saying that because this Bunch-Davies is an entangled state of this L and R vacua, which appear here. So that's just the same way that Maldacena computed the entanglement entropy for exactly this picture, and I'm just computing the complexity between this L and R vacua. So that's long range because that's exactly why it's not divergent as the UV cutoff, because I'm not computing the Minkowski vacuum part of this computation. I'm computing something that is that is symmetric under the transformation of the L regions. So this is a 3-1, I guess. So that's, in that sense, it's long range because these are separated by, these are causally disconnected paths. So that's the long range interactions.
Okay, I see. Thanks.
Okay, thank you very much. Let's thank the speaker again.